very fortunate to have to be speaking after the last two talks, because the discussion and the concept of the habitable zone is important as a prerequisite for what I'm going to be speaking about. And I want to acknowledge that this is work done with collaborator Peter Biermann. So first of all, we can look at the habitable zone concept, circumstellar habitable zone concept, and this, as Manuel spoke the other day on, is really a classical concept, because just simply being in the so-called habitable zone around a star does not make a planet habitable, because very often there are other effects. But this is a useful concept, and has been a very useful concept, because it has allowed us to at least place this as a necessary condition for the kind of life that we have on Earth. And as this was spoken about before, I'll just briefly mention that stars are formed often with rapid rotations. They evolve to rotate slower due to magnetic braking. The activity on the star is closely related to the environment that the planet will experience. As time progresses, the stellar activity, the magnetic activity, decreases because the rotation of the star slows down, causing a less vigorous dynamo in the convection zone, and less coronal activity. This is also an effect that is very important when you consider stars of various types, because as was also discussed, M stars are more active, not in an absolute sense, but as a sense of the total luminosity of the star. More of it is in X-rays, and these activity will last longer on lower mass stars, because they take longer time to evolve and reach the main sequence. But so in this picture we show the sunspots, which implying magnetic activity, and the rotation of the stars is depicted as slowing down. But one thing I would like to just pose as a question that I will address later on is that, is there a way to reduce the rotation of the star during the first giga-year after formation that would reduce the mass, the water loss, the atmospheric loss from planets? We'll address that in a little bit. So, as I've described, this is a useful concept, but it's certainly not a sufficient requirement for planets to be in the habitable zone of their star. We must consider the effects of X-ray and extreme ultraviolet conditions, as well as cosmic rays, as I will describe, and also, of course, all of the geological properties and atmospheric properties. Certainly, we don't, the moon is not habitable yet. It is in the habitable zone of the sun. So this is a classical concept that we need to think about, and is useful, but we need to move on beyond that. And the same as was said in the last talk, that we have a similar effect with the galactic habitable zone. It's a useful concept, and we can proceed with it, but we also have to take it with some grain of salt. The galactic habitable zone and there's some papers here that have developed this idea from the beginning, and as mentioned, a lot more work is being done on this recently. And one concern that I have is that as we progress with this, we need to think about it in terms of going to other galaxies and thinking about galactic habitable zones around other galaxies is a little bit more problematic than because of our own galaxy. Now, the reason for this is our own galaxy has a supermassive black hole in the center of it. However, it is quite low in activity, and other galaxies have much more massive supermassive black holes, and they are very often more active. And we, even in our own galaxy, certainly the supermassive black hole that we have has historically not always been as inactive as it is now. So the hypothesis we have here is that life, especially advanced life on the surfaces of planets, was impossible or extremely rare until soon before the formation of Earth. And a lot of this argument follows along what Charlie was describing, how the universe has evolved and the opportunities for life on planets has evolved with that. So exposure to planets to ionizing radiation, both persistent and stochastic, has decreased many orders of magnitude over the life of the universe. Potential planetary protection is also substantially increased. The argument for that is that the density of both galactic cosmic rays and extragalactic cosmic rays is dramatically higher in the past for these reasons. First, the size of the universe is increasing, so it was much smaller in the past. This exposed planets to the cosmic rays, especially ultra high energy cosmic rays, which can leave the galaxy and penetrate our own by a couple of orders of magnitude. Star formation rate, the supernova rate, were both much higher in the past and has decreased by at least one more order of magnitude in the last 5 or 6 billion years. AGN activity was higher in the past, producing more ultra-high energy cosmic rays, as well as radiation. And those environments are especially harmful for planets in those galaxies, but not only for those galaxies, but also for nearby galaxies and those that are in clusters. Not only that, the protection has improved. We have ways to protect the Earth from the cosmic rays, and the increase in the carbon, nitrogen, oxygen elements, iron abundances have provided planets with atmosphere, or the potential to have atmospheres that are thick. And iron and silicates are needed for dynamo to produce the magnetic field generation, which protects planets from cosmic rays, as well as from the high energy radiation, the high energy particles from the sun. As well, the galactic magnetic field has improved over the lifetime of the galaxy. This is due to the supernovae rate that provides galactic magnetic shielding from the extragalactic cosmic rays. So first of all, we'll look back at the picture here showing the iron abundance, and we need to be near we need to be in the thin disk in order to be considered to have the proper elements and able to form the cores, and the radioactive elements are also quite critical, as was mentioned. Another way to look at this is where we see that the only region of the galaxy, the halo doesn't work, the thick disk doesn't work, and the bulge, well, maybe some stars in the bulge, but in the thin disk, it's the only place where we have the iron abundance that is sufficient for planets that are truly Earth-like. If we look at this schematic, which shows our galaxy and the sun's location, the metal content far from the midplane, the sun, it's hard to see here, but the sun has significantly more metallicity than the stars far from the midplane of the galaxy at all distances, galactic-centric distances. So it's not only important, and I think that this is a concept that should be added to the concept of the galactic habitable zone, because it's not only the stars and the galactic-centric distance, but how far away from the plane they are. They need to be generally formed more recently and in the galactic plane. There are plenty of stars in the solar neighborhood, for instance, that just don't meet this criteria. Close to the midplane, the metal content of the sun is more like the inner part of the galaxy and quite a bit less like the outer part of the galaxy. So considering three types of high energy particles that interact with the Earth's atmosphere, producing air showers, we can break those into three groups: the extragalactic cosmic rays, which are from sources that have black holes, that have large amounts of star formation activity, like M82. And today, within about 20 megaparsecs, there are many, many supermassive black holes, and those can affect the habitability of planets not only within those galaxies, but in nearby galaxies as well. The galactic cosmic rays, these are the most common, typically what people think of as the cosmic rays that are generated by supernova remnants. These remnants around supernova will accelerate cosmic rays to very high relativistic speeds and impact the Earth. And in addition to that, the galactic supermassive black hole, microquasars, which are black holes, will also be a supplier of these cosmic rays that can be significant for life. And I need to stop for a second and say, well, I'm really concentrating here on surface life. I do agree that unless you're able to remove the water from the planet, that marine life is not subjected to this. The stars have energetic particles also, and I am in the camp that is strongly in thinking that the M stars are not very suitable for habitability precisely because of this activity and these solar energetic particles that will remove the water from the atmosphere of planets, unless, of course, the atmosphere is quite thick and has a suitable composition. So in the Medal diagram that Charlie was describing before is a similar one. Here shows how the star formation rate has decreased. Earth forms on this declining branch here, and we're located here. So even in the time since Earth formation, the star formation has decreased. Star formation rate has decreased substantially, and the cosmic ray density has likewise decreased, because these cosmic rays, after they get accelerated by supernovae, stay around for roughly 10 to the 7 years before they leak out and become part of the galactic wind. As If we consider the starburst galaxy in M82, the cosmic ray density for planets exposed in M82 is up to 3 orders of magnitude higher than what we experience here on Earth. And if we look at the supermassive black holes and galaxies, we have some local neighbors that I call bad neighbors here. Currently, we don't receive too many high energy cosmic rays. And let me emphasize that these are often relativistic iron nuclei that can cause a lot of damage. They can heat grains in proto-planetary disks and in the interstellar medium. They can remove water from those grains. And if Centaurus A were to accrete at just slightly above Eddington, then the flux would be 10 to the 5 of what we have now, 10 to the 3 more cosmic rays than we experience here. And this is because of a supermassive black hole in another galaxy. So you could think about other cases. Here's M87. Its current output corresponds to 100 times Centaurus A. By the way, M87 is a giant elliptical galaxy in the core of the Virgo cluster of galaxies. And so if it were to go 10 times Eddington, its output in terms of cosmic rays would be 10 to the 5th, the current from Centaurus A, about 10 to the 3 times what we are experiencing here, again from a supermassive black hole that is quite far away relative to our own supermassive black hole. So, well, in our own galaxy, during the past 3.5 billion years, we know that there hasn't been a sterilizing effect from our own supermassive black hole. However, we have to consider that we have a fairly low mass supermassive black hole in the Milky Way, and we are 8 kiloparsecs away from it. And so it potentially could cause major problems, and these problems occur most often during mergers when the accretion onto the black hole could be very significant. We know the Milky Way has undergone a number of mergers with dwarf galaxies. There is evidence for that. There are fingerprints in the stellar population. But so far we've survived that. If it did go super Eddington, the cosmic ray problem would be very significant. The relative to current day cosmic ray levels is between 10 to the 5th and 10 to the 6th. So how could this be avoided? Well, one way is in binary star systems, as was described, that binary star systems do have habitable zones, but they also have increased winds. And the winds from stars allow for the protection by building a hydrogen wall, stellar astrosphere around the planetary system to protect from cosmic rays below a certain threshold. And I'm running out of time, so I won't discuss this further, but the additional effect of binary stars is because the binaries, stars and binaries can be close enough to tidally interact with each other, the rotation of the stars may be affected, and if the binary period is between 10 and about 40 days, the period of the binary will, the period of the star rotation will begin to change and seek that period of the binary, reducing the activity of the star, that effectively prematurely aging the star. And I'll skip that one and just say, well, the future for habitability, we've got satellite galaxies that will be merged. Eventually, the Andromeda galaxy in about 4 billion years, will merge with our own galaxy. This could be a serious problem. The most serious problem comes from the merging of the supermassive black holes themselves, as the radio jets will change direction and cause really major havoc throughout the galaxy. I don't think any part of the galaxy is safe as a result of a merger. And I think this is a quite an interesting thing, because one of the factors is to have habitability, you need planets. And the globular cluster 47 Tuc is considered one of the more metal-rich galaxies. It's still quite metal-poor compared to the Sun. But in a study by Gilland, they found that there were no Jupiter mass planets in their, that came out of their study. They expected to have something like 17 Jupiter mass planets observed from an HST study, radial velocities of stars in this globular cluster, and found none, which implied very strongly that the number of these planets in 47 Tuc is an order of magnitude less than what we have here. One of the reasons has been proposed that rapid star formation, so I want to focus on this, that rapid star formation in dense clusters and in galaxies, compact galaxies especially, in bulges, can be UV photo-evaporated, so that the disk itself is evaporated, not allowing the planets to form in the first place. And I'll conclude with that. Thank you.
Thank you.